All right, let's go ahead and get started. I want to welcome you back to Unit 12. This is acids and bases. And I thought a good way to kind of bring this unit to a close was with a couple of challenge questions. So these are really going to test our understanding of this unit and make sure that we know what we need to know. So let's take a look. Number one says this. Well, we're given this data. So let's take a look at the data to begin with. And here's what it says. We've got three different acids. We've got hydrochloric acid, we've got acetic acid, and we've got nitric acid. So three different acids. The concentrations vary. We've got 0.1 for the hydrochloric acid, 0.1 molar for the acetic acid, and 0.2 molar for the nitric acid. So the nitric acid is the most concentrated of all. And by the way, we need to understand that concentration is not necessarily related to the strength of the acid. In other words, strong acids are not concentrated and weak acids not dilute. Those are two different issues. So you can have a strong acid that is dilute, or you can have a weak acid that's concentrated, okay? So let's take a look at the pHs. The pH of the hydrochloric acid is 1.2. It's low as we would expect. The acetic acid, 3.4, still in the acidic range, but not quite as acidic as the hydrochloric acid. And the nitric acid has a pH of 2.1. And they're telling me in terms of electrolytes, in other words, the ability to transmit electricity. Hydrochloric acid is a strong electrolyte. That means it's a strong acid, as is nitric acid, a strong acid. But acetic acid is a weak acid because it's a weak electrolyte. It doesn't conduct electrical current very well. So let's take a look at the question now that we have looked at the data. It says the pH of a 0.1 molar acetic acid solution is 3.4. Well, they're not telling me anything that I'm not seeing in the data. The pH of the acetic acid is 3.4, and it says the pH of the 0.1 hydrochloric acid is 1.2, again, in the data. So it says, how can these acids have the same molarity but have different pH values? What we want to try to do is we want to try to arrive at the answer in our heads before we look at the answers, because once we look at the answers, everything's going to look right. So again, let's read the question one more time and see if we can, just from the question, derive what the answer is without looking at the individual answers. So it says, how can these acids have the same molarity, 0.1 and 0.2, but have different pH values? Obviously, the hydrochloric acid has a lower pH value than the acetic acid. Well, I think that it's going to be because of the hydrochloric acid being a strong acid. It has to do with the fact that hydrochloric acid is completely ionized. In other words, if you take hydrochloric acid, HCl, and you put it into water, what you're going to get is you're going to get H plus, and you're going to get Cl minus, and you're going to get those exclusively. In other words, there's not going to be anything left of the hydrochloric acid. That's what we mean by a strong acid. But acetic acid is a weak acid, which means this, which means that if you take the acetic acid, and the formula given to us for acetic acid is this right here. Let's see, that's C2H2O2, H3O2, just like that. And it dissociates, it does not dissociate completely. In other words, this is what we call an equilibrium. But some of the acetic acid is going to dissociate into H plus ions, and some will dissociate into acetate ions that look like this. Okay, just like that. So, but the point is that it's not a complete process. The arrow doesn't just go to the right, it goes back and forth, and it's an equilibrium. So not all the acetic acid is going to dissociate. But what determines the pH? The pH is going to be determined by the hydrogen ion concentration, isn't it? Remember that pH is equal to minus the log of the hydrogen ion concentration. So even if you had the same concentration of the HCl as you do of the acetic acid, if you started with a 0.1 molar solution of this and a 0.1 molar solution of this, you're not going to get the same amount of H plus as you do here You're going to get more H plus here than you do here. So H plus in higher quantity is going to drive the pH down, right? So a lot of hydrogen ions are going to make the pH go lower. So we'll just make an arrow like that. As opposed to this 0.1 molar acetic acid situation where hydrogen ions are produced, just not in as much quantity as in the equation above, right? So that's it. That's my answer. So let me just kind of recap what I've come up with. What I'm saying here is that because of the fact that the acetic acid is a weak acid, that it's not going to produce as much hydrogen ion as is the hydrochloric acid at the same concentration. So you're going to have more H plus, and therefore the pH we would expect to be lower, and it is. So let's now look at the answer and see if we can determine from what we've kind of rationalized, or what we've intellectualized, what the correct answer is. Let me read the question one more time. How can these acids have the same molarity but different pH values? So let's see if we can find one of these answers that matches what we've just said. A, the hydrochloric acid is more concentrated than the acetic acid. Well, gee, hydrochloric acid's concentration is 0.1, and so is acetic acid. That cannot be the right answer. Let's knock that one out right now. The next one, B, says acetic acid produces 2 H plus ions. Hydrochloric acid produces 1 H plus ion. Well, no, that's not true. Acetic acid has only one acidic hydrogen, and that's this one right here. This hydrogen that's shown here is the only one that's going to be removed. The other hydrogens are not what we call acidic hydrogens. They're not going to go away. So we'll take that one out as well. The next is hydrochloric acid is a weak electrolyte. I'm going to stop right there. Hydrochloric acid is not a weak electrolyte. It's a strong electrolyte. It says that on the table. Don't worry about that one. It can't be right. So let's take a look at the last one and hope this is the right one. D says nearly all of the hydrochloric acid dissociates, little acetic acid dissociates. Well, that's more in line with what we were saying in our answer. Hydrochloric acid is a strong acid. That means it's going to dissociate completely into hydrogen ion. Whereas acetic acid is a weak acid, so little of the acid dissociates. We're going to put as our answer, with a great amount of confidence, letter D. And that'll do it for the first one. All right, let's take a look at the second question. It says the diagram below shows the structure of a common pain reliever. This is an EOC released question. Now, first of all, don't let the structure scare you. This is what is called an organic molecule, and those little lines indicate the bonds between carbon atoms, and carbon and oxygen, and carbon and hydrogen. But this is something we'll look more in depth in AP chemistry, but we can still answer this question if we know what the definition of a Bronsted-Lowry acid is. So what do we mean by a Bronsted-Lowry acid? So they're showing us this molecule. So let me just give you a little bit of a background. Everywhere you see a corner, there's a carbon there. So there's a carbon there, there's a carbon there, there, and so forth. Okay, everywhere you see a carbon, a corner, there's a carbon. And these represent double bonds here, right? And this is like carbon-oxygen bond and so forth. So the point is this. The point is that you can determine the answer to this question even though you don't know anything about organic chemistry. You simply need to know the definition of a Bronsted-Lowry acid, okay? So let me just give you a little bit of a background. It was in 1923 that Johannes Nicholas Bronsted and Thomas Martin Lowry independently defined acids, Bronsted-Lowry, what they call Bronsted-Lowry acids, to be proton donors, okay? To be proton donors, and bases to be proton acceptors, as opposed to the Arrhenius definition, which was previously said to be an acid was something that increased the hydrogen ion concentration, and a base was something that increased the hydroxide ion concentration. So you have to have those two in your mind solidly, okay? So Bronsted-Lowry said that an acid then, a Bronsted-Lowry acid, is a proton donor. Well, where do you see a proton on here? Where do you see a hydrogen atom? Right there. This position number 2. That hydrogen atom is going to be released as a proton at some point. So the only place that hydrogen exists is that second position. And so our answer to the question, which one is a Bronsted-Lowry acid? It would have to be position number 2. That's our answer. Okay? All right. Let's take a look at this last question now. Adding vinegar or acetic acid to water causes the hydroxide ion concentration to do what? Okay? So, first of all, I expect you to know that vinegar is acetic acid. That's first of all. I also want you to know that acetic acid is an acid. That should be self-explanatory just from the name. Acetic acid is an acid. So what I wanted to do was kind of diagram a scenario of what might be happening if we had water, right, and we add acetic acid to it. So on this left-hand beaker, all right, or my drawing is terrible and I apologize, but that's the best I can do. This is a beaker on this left-hand side, and it's got water in it. So what does water really have? What if we could see it microscopically or atomically? What would this look like? What would the water look like? Well, certainly we would have water molecules, right? We would have H2O molecules floating around, and I've showed those here in this kind of deep purple color here. But we would also have some dissociated water. We'd have some H plus and some OH minus. So we show those. I show those in the light blue and the kind of the lime green there, right? And there would be, of course, this is just representatives because I would have millions and millions and millions of these, right? So millions and millions of H2O, millions and millions of H plus, and millions of OH minus, just like that. But what happens if I add CH3COOH, acetic acid? Well, what's going to happen is that the acetic acid is going to dissociate into the water, right? And so what I'm going to get is, in the dissociation process, I won't draw it in the beaker, I'll draw it down here, is I'm going to get these two things. I'm going to get CH3COO minus, but I'm also going to get H plus ions, right? H plus ions. And so when I get those H plus ions, what's going to happen is that those hydrogen ions are going to associate themselves, in some cases, many cases, with the OH minus ions that are freely floating around that I've already demonstrated to you. And they're going to form water, right? So the hydrogen ions are kind of being gobbled up. Or sorry, the hydroxide ions are being gobbled up by the hydrogen ions to form water, right? Which is neutral. So to answer the question, what happens to the hydroxide ion concentration if I add acetic acid? It's going to decrease, is it not? It's going to go down because of the fact that I'm adding hydrogen ions to this mix, this situation, right? I'm adding hydrogen ions through the acetic acid and therefore causing the pH to go down, and the hydroxide ion is increasing, right? The hydroxide ion concentration is decreasing because the hydroxide is being gobbled up by the hydrogen ions that are in the solution, giving me water and making the solution more acidic. So, folks, I just wanted to take a look at 3 questions. These are challenge questions that are going to really deepen our understanding of acids and bases. We're definitely not through yet. We're going to finish this unit right now. This is going to be at the end of Unit 12. But I want to have another unit called acid-base equilibrium and buffers a couple of units from now. So be on the lookout for that. But we really need to study equilibrium a little bit before we get into that. So be on the lookout for another acid-base unit that we're going to call acid-base equilibrium. I'll see you on that one. Thanks. Bye-bye.